Hello again. This is a video on chapter 3. I'm gonna try to finish chapter 3 in this video. The sections that we're gonna talk about are these sections: inverse functions and the absolute value functions. Those are the sections. So let's start. I'm going to first again get rid of my video here. We don't need that. And then I'm going to open up that problems from section 3.6 and 7. So let's go to chapter 3. No, not that one, but this one. New chapter. All right, so let's see. Okay. So this is the one that I want. This is the one that I don't want. Okay. So let's do some of these problems. So what we want to do is, let's say, number 5 and 6. So what are we supposed to do? Well, we are supposed to talk about absolute value. So let's do that. So what I'm going to do is talk about what absolute value is, first of all. I think we already know, but it's good to review it a little bit. So when we when we use this symbol, two little segments like that, that's of course absolute value in mathematics. An absolute value of a number means the distance from 0. So if this is 0, so for example, absolute value of 2 means how far it is from 2 to 0, and that is, of course, 2. And absolute value of negative 2 means how far it is from 0 to negative 2, which is again 2. That's one way to think of absolute value, and it's a good way to think about it. So for example, when I write 5 minus 2 in absolute value, it means the distance between 5 and 2. The same is 2 minus 5. 2 minus 5 is the distance from 5 to 2. 5 minus 2 is the distance from 2 to 5, which is basically the same. Both of these would be, this would be absolute value of 3, which is 3, and this is absolute value of negative 3, which is also 3. So when we write absolute value of A minus B is basically the distance from A to B. Now, usually if this one is unknown, one of them is unknown, we write it first. So for example, how do I write the distance between a number and 2? Well, distance between a number and 2 would be that, right? And when we talked about absolute value equations, I think in other videos I talked about this, but in this section we want to talk more about it as a function. So for example, when we write f of x equals to absolute value of x, what do we mean by that? We mean we have a function where the input is any real number and the output is basically absolute value of that number. So that means any number you enter here, the number here would be absolute value of it. So if we put a 2 here, 2 comes out. If you put a negative 2, 2 comes out, and so forth. If you graph such a function, 0 goes to 0, 1 goes to 1, negative 1 goes to 1, right? And so forth. 2 goes to 2, and so forth, right? And negative 2 goes to 2 again. So you see, you get like kind of a V shape. I missed that a little bit, but it's a V shape like that. So absolute value function by itself looks like that. Well, we can transform it and graph it. We know about transformations, right? So here you go. It says describe all numbers x that are at a distance 4 from the number 8, expressed using absolute value. So we want to describe all numbers x whose distance from 8 is equal to 4. That's it. That's how you describe that, right? It's this equation right here. Okay. Describe all numbers x that are at a distance of 1/2 from the number -4. So here a number, the distance means you have to take the difference between x and this number. So x minus -4, the distance between x and -4 has to be 1/2. Now, of course, x minus -4 is x plus 4 inside the absolute value and equals to 1/2, right? So that's the idea. Let's do a few more. So let's do number 7 and 8 as well, now that we are at it. There you go. Now, 7 and 8, the question is, let's get some areas here. So the question for 7 and 8 is that describe the situation in which the distance that point x is from 10 is at least 15 units. Now, at least means what? Means that you want it to be 15 or more. So you want it to be equal to 15 or greater than 15. What has to be 15 or greater than 15? Well, the distance between x from 10. So that means the distance between x and 10, right? Which is written as that, right? That's the idea of this number. Number 8, find all functions, function values f of x such that the distance from f of x to the value 8 is less than 0.03. Now, we want the distance not from x to 8, but from f of x to 8. So we need to write f of x minus 8, the distance between f of x and 8, has to be what? Less than 0.03. Less than 0.03. That's it. That's how you do that. All right. So that's number 7 and 8. Let's do one more of these. Number 10 says find the x and y intercepts of the graphs of each function. So what do we want to do? We want to find the x and the y intercepts. So let's do that. Now we know that we want to do number 10. So let's see. So we want to do this one right here. Now we know x-intercept is when x equals to some number and y is 0. Y-intercept is when y equals to something and then x is 0. So f of x equals to -3, x minus 2, minus 1. Well, the y-intercept is the easier one to find. The y-intercept is f at 0, which is basically negative 3, 0 minus 2 minus 1. So that's negative 3, absolute value of negative 2 minus 1. Now don't multiply. This is not parentheses, right? This is absolute value. You have to do this operation first. So that's negative 3. What's absolute value of negative 2? Positive 2. Now you can multiply, because we are not allowed to multiply here. This is negative 3 times whatever the value of absolute value is. This is not a parenthesis. You can just go distribute it. Now you can multiply. So that's negative 6 minus 1, which is negative 7. So the y-intercept is 0 and negative 7. Now what is the x-intercept of this thing? Well, the x-intercept is going to be when f of x equals to 0. That means negative 3, absolute value of x minus 2, minus 1 equals to 0. So it means that negative 3 absolute value of x minus 2 equals to 1, and absolute value of x minus 2 equals to negative 1/3, right? Now, can this be true? Can absolute value of something be a negative number? No. So this has what? This has no solution. What does that mean? Well, it means that it doesn't have what? X-intercept, right? It doesn't have x-intercepts. If we did everything correctly. Did I do everything? Did I put? Yeah, it is negative 3. So now, how can we graph this? We're not asked to graph it, but we can graph it. You just have to think of what, if you were to graph this, you would have to think of just a regular absolute value, which looks like what? Which looks like this, right? And then what? Then pick three points, 0, 0, maybe 1, 1, and then maybe negative 1, 1. And then use this transformation. What's this transformation? Well, think of this as old y. So if I have a, and let's call this g of x is absolute value of x. So if I have a and I have g of a, then where does this go? Well, it's going to go to what? Well, it's going to go to negative 3 times g of a minus 1. So negative 3 g of a minus 1. And then the x is really x minus 2 has to equal to what? Has to equal to a. So x is a plus 2. So this is a plus 2. So that means what? That means, I'm going to write here so I can use this space. So 0, 0 is going to go to what? Well, 0 plus 2 is 2. And negative 3 times 0 is 0, minus 1 is minus 1. So 0, 0 go to the, let's graph it here. So 0, 0 goes to 2, negative 1. 2, negative 1. There. So this vertex right there is right there. And then what about 1, 1? 1, 1 goes to, well, 1 plus 2 is 3. And so 1, 1. So if I put, If I put 1 for a here, 1 plus 2 is 3. Now I have to put 1 for g of a. So this whole thing is just 1. So negative 3 times 1 is negative 3 minus 1 is negative 4. So this goes to 3 and negative 4. 1, 2, 3, 4. There. That's where it goes. And then what is the y-intercept that we found? Remember, it has a y-intercept. We got it somewhere over there. It was negative 7. You see that? So y-intercept is negative 7. So let's do that. So that's 1, 2, 3, 4, 5, 6, and 7. So that's the y-intercept. And now, where is the other one? 1, negative 1 go? Negative 1, 1. Where does that go? Well, negative 1 plus 2 is 1. And 1, negative 3 times 1 is negative 3 minus 1, negative 4. So here's 1 and negative 1, 2, 3, 4, and 1 right there. Right? Oops. There. So this V shape is now over here, and we know the y-intercept was right there somewhere. It's kind of right there. And that's the graph, right? All right. So that was number 10. So let's do one more, number 16. It says, for the following, graph the absolute value function, plot at least 5 points by hand. Well, this is easy to graph because this is just what we can use transformations, or you can use points. It's up to you, but we're going to use transformations. So, where did that go? All right, here we go. So if you use transformations, we know that the original graph looks like a V like that, right? Kind of like that. So what happens to it? What transformation is this? Move to the right 1 unit. Everything goes to the right 1 unit. So you can move it to the right. Just put 1 on the x-axis. Don't put any other points. Don't mark any other number. And graph it. Then you can find the y-intercept and put a number there. What's the y-intercept of this? Well, the y-intercept is when x equals to 0. So its absolute value is 0 minus 1, which is absolute value of negative 1, which is 1. So this number has to be 1, and we're done, right? You could also use points if you want. You can make a table, just some positive numbers, some negative numbers, and graph it, right? You can make a table, just get negative 2, negative 1, 0, 1, 2, and then absolute value of x minus 1, and see what you get. So you can graph it that way. So let's do number 22. Do number 22. Okay, so here is number 22. Well, we graphed one already, but let's graph this one too. Let's do it using transformations again. So what I can do is just use this space that we are given here. So that would be, this would be the graph of, so if we make this, complete this xy coordinates, right? So the function is y equals to negative x minus 3 minus 2. So what we have to do is, if we have a point here, 0, 0, where does that go? So we can again move the 3 points, 1, 1, negative 1, 1, right? Negative 1, 1, 1, 1, and 0, 0. Where do they go? Well, let's see. If we have a and let's call this, g of x. So we can name this g of a. So every point on that original graph goes to, well, look, again, this part is the old y, right? So it's negative g of a minus 2. Negative g of a minus 2. And the a part, x minus 3 equals to a. So x equals to a plus 3. So a plus 3. So 0, 0 goes to 0 plus 3 is 3. Negative times 0 is just 0. Minus 2 is minus 2. So this point goes to 3 minus 3 negative 2, which is this point right there. And then where does 1, 1 go? 1 plus 3 is 4. And negative 1 minus 2 is minus 3. So 4, negative 3 is that point right there. And then negative 1, 1 goes to, well, negative 1 plus 3 is 2. And negative 1, this g, the whole g of a is just 1. Negative 1 minus 2, again, negative 3. So 2 and negative 3, which is this point. And we could just graph this part. And what is the y-intercept of this? The y-intercept is when x equals to 0. So y equals to negative 0 minus 3 minus 2. So that's negative 3 minus 2, because this absolute value of this whole thing would be 3. And this is a negative here, negative 3 minus 2, which is negative 5. So the y-intercept is negative 5. So that's what it looks like, right? All right, and that was the last one. No, you can also use the one with a calculator. Let's do it to 32. And see, use a calculator to graph. There you go. It says use a calculator to graph that on viewing window of that, identify the corresponding range. So show the graph, okay? So to graph this, we need to go to y equals to and put 10, 10 times absolute value of x minus 2. Now absolute values under math, number. See, the first one says absolute value. You fetch that. And that means absolute value of x minus 2. So you put x minus 2 in there. And now we want to make a viewing window 0 to 4. 0 to 4. And now the corresponding range that we should put is what? If x is 0, that would be 10 times 0 minus 2. So that would be positive 2 times 10 is 20. So the y min would be 20. And the y max would be when x is 4. 4 minus 2 is 2. It's still 20. So really, we need to go from, both of those are 20. So let's say from 0 to 30 is good, right? 0 to 30 is good. And let's graph this. and that's what it looks like, right? So we graphed it from 0 to, because we know the y values for this x and for this x would be both 20s. So we just go from y min to y max a little bit more than 20, maybe. Now, if you want to go exactly 20, you just put exactly 20 from 0 to 20. And we're going to get exactly that graph right there. Okay, so that's how you graph with a calculator. Now, of course, you could go to Zoom 6. It graphs it only in 10 by 10 window. Zoom 4 it graphs it in a smaller window, and so forth. All right, I think we are done with this section. So let's go and let's do the last section, which is about is 3.7. So we want to talk about inverse functions. That's what we want to do. Inverse functions. Okay, so and we're going to start with, first of all, make it a little bit bigger. That's good. I'm going to start with 8 and 12. All right, now before we do it, I want to do 8 first. So in these problems, we need to find the inverse of this function. But before we do that, let's talk about what inverses are. So what we mean by an inverse is what? Well, if you have a function, let's say we have a function or relation, doesn't matter. Let's say 1, 2, 3, and 4, 5, 6. Remember these examples when we talked about functions and relations in previous videos? So this is a relation. So basically this is the x value and this is the y value. So 1 is related to 4, 2 is related to 5, 3 is related to 6. Now, if you switch x and y, but still name the first one x and name the second number y, but use what? Use these numbers for x and use these numbers for y. This is the inverse of that relationship. So here 1 goes to 4, 2 goes to 5, 3 goes to 6. Here 4 goes back to 1, 5 goes back to 2, and 6 goes to 3. So these are inverse relations. But remember, this relation is a function, right? Because input doesn't repeat. This relation is also a function. So we can say these are inverse functions because both of them are functions, right? But notice that if we have a function like this, then if you switch x and y, then its inverse is not what? Is not a function. This is not a function, right? Not a function. It is the inverse of that, but the inverse, we can't call it a function. So we are interested in functions whose inverses are what? Also functions. So that means if you have a function like this is good, but a function like this, well, not so much, because when we take the inverse, it's not a function. So the functions whose inverses are also functions are called one-to-one functions. One-to-one. And you know why? Because there's one input, one output, one output, one input. It's a one-to-one relationship. That means neither the input nor the output repeats, right? So to find a one-to-one function, to figure out whether a given function is one-to-one, all you have to do is look at what? Now, if you assume that is a function already, you don't have to worry about the input. But if it's a function, but the output repeats like this one, then this is not what? This is not a one-to-one function. Now, what if you're given a graph of a function? For example, you think the square root of x is a one-to-one function? Yes. Now, is it a function? Yes. How do we know? Because we can tell there is no input repeating if we test it with a vertical line test. How do we know there are no output repeating? Well, we can use the same trick, but this time, instead of vertical line, we scan it with a horizontal line. If there are more than two intersections, more than one intersection, if there are two or more intersections, then we say this is not one-to-one. For example, this graph right here is not one-to-one. Why? Because these two have two different input, but the same output. So this is not a one-to-one function, but the other one is a one-to-one function. Okay, now if you're given an equation and asked whether it's one-to-one or not, look at its graph and then figure out from the graph. This is not a one-to-one function. All right, now the question is, how do we find the inverse of a function? So before I do number 8, I'm going to do some more work down here, and then we go back and do number 8. So if I give you a simple function, let's say f of x equals to x plus 2, what does this function do? Well, it takes the input and gives you an output. How does it calculate the output? Well, it's x plus 2, right? So now the question is, what's the inverse of this function? So the inverse of this function will be anything that, for example, let's say input 3 here, then the output would be 5, right? So what I like is a function that takes the input like 5 and gives me the input back. So I take the output of this function as an input of this function, and then the function gives me the input back. That's the inverse, right? 3 goes to 5, and then this function takes 5 and gives you the 3 back. So what do I put in here? Well, we can kind of tell what happens to x here. You add 2 to it. So basically, to cancel it, you have to subtract what? Subtract 2. Now, we can't call this function f of x. We have to call it something else. So we can go look for notations for it, but it would be a waste of time because people already decided what notation to use. So we're going to use their notation. So what we're going to do is, we want to use this notation. We put f, you put -1 here on the exponent. Now, f to -1 could mean 1 over f. But this is not what we mean by this. In this context, when we write this, we read it like f inverse of x. That's how you read it. F inverse of x. That means this is the inverse function for the function f of x. All right. Now, a few things if you can notice is that, first of all, let me write a few features of this. Number 1 is that, what's the domain of this function? Would be all real numbers, right? And the range of this function also is all real numbers, because this function is what? This function is a line. Now, what is the domain of the inverse? Well, domain of the inverse is actually the same as the domain as the range of the function. Why? Because you switch x and y. Remember, domain here is basically x values. That's the set you get the x values from. And the range is the set you get the y values from. So when you switch x and y to find your inverse, then the range becomes the domain and the domain becomes the range. So the range of f inverse will be the same as the domain of f, right? So that's the first property of inverses. Let me put the number 1 here. So that's the first property of inverses. The second property of inverses has to do with composition. So if we take f and then put f inverse inside, like that, what do I get? Well, let's do some scratch paper here. Scratch work here. So if I take f inverse and put it in f, so what is f? F is, so f of f inverse of x would be, if I take f, which is input plus 2, and put the inverse in it, which is x minus 2, what do I get? Well, I get x minus 2 plus 2, which is x. And this always happens. If we have two inverse functions, this always happens. And also, when we take f inverse and put f in it, what do we get? Well, let's see. So if we take f inverse and put f in it, what do we get? Well, f inverse says input minus 2. So input minus 2. And if I take f of x, which is x plus 2, and substitute it here, what do I get? X again. And this is always true. So that's another property of inverses, that if you compose the two inverses, you get x in either order, right? And that shouldn't be very surprising because they cancel each other, right? So if they cancel each other, then it shouldn't be surprising that you get, that you get this result. So now I also want to explain a little bit more what's going on. If I can erase this. All right, so why is this happening? Well, think about it. This is f of x. Let's say this is, I put 3 in here, and 5 comes out, right? This is x plus 2. What happens if I take this 5 and put it in f inverse, x minus 2? Well, I get 3 back, right? This is like what? I take f of x and put it in as input for f inverse. So it would be this one. That's the example right there. Now, what about this one? Well, this one is if you start with what? If you start with x inverse, the f inverse, x minus 2, and then let's say we start with, let's say 4, right? So 4 minus 2 is 2, and then let it go through what? Through f. What comes out? Well, 4. You get the 4 back. So whatever you put in here comes out because these two, this one and this one, cancel each other, right? Whatever this one does, this one undoes, so 4 comes out. Now, something happens to 4 is not like nothing happens to 4. Something does happen to 4, except for that when it comes out, it looks like nothing has happened to it, because whatever happens gets canceled. Same is true here. All right, so that's the property of, now I realize why I didn't erase, because you have to use the other end. All right, now I know. to use this end. Okay, so now what's the third property of inverses? Well, the third property is that if you graph these functions, let me graph these functions. So x plus 2 is like 1, 2, you go to 2, that's 1 point. And then the slope is 1, so you go up 1 and right 1, right? And you get a line, that's that graph. And the other one is x minus 2, so you go to 2 here. The slope is still what? 1, so you go up 1 and right 1. And you're going to get this line. And these lines are, whoops, these lines are going to be, of course, what was that? That was negative 2 up, right there. So these are kind of parallel, as you see, because they have the same slope, right? But one thing you notice is that if you graph y equals to x in the middle, y equals to x, remember, is a line that goes through what? Goes through quadrant 1 and quadrant 3, y equals to x. So these two graphs are symmetric with respect to this line. And this is always the case. So number 3 says that the graphs of what? Let's write it down. Graphs of f and f inverse are symmetric with respect to y equals to x. Okay? And it shouldn't be surprising either, because remember, let's say this is 3 and 1, right? And here is the line y equals to x, right? Y equals to x. Now, 3, 1, if you switch x and y, you go to 1, 3, right? See? 1, 3. And this always happens, right? So the points that are on the line don't go anywhere, because when you switch x and y, and the points on this line, x and y are equal. So if you switch x and y in any other point, you just jump to the other side of this line. Any point on this line stays put, right? But this point jumps over there when you switch x and y. So that means if this is a function, this is the inverse, they are what? They are symmetric with respect to what? Y equals to x. For example, this point and this point, right, are symmetric. And if it happens to all the points, then the whole shape is symmetric. All right, now we can go and talk about how to find the last thing I want to do, and then we do number 8. So suppose this was easy to find the inverse, but how do we find the inverse in general? So if you are given a function, to find the inverse, what we do is we first make f of x, y, and then second step is we switch x and y. So basically everywhere in the equation that you see x, put y, you put x. And everywhere that you see x, put y, right? There, see that? Okay, and then solve for y, right? And set equal to F inverse. There. Okay, so what do? Basically, we solve for y here. So solving for y, we get y equals to x minus 2. Just move the 2 to the other side. And so F inverse is going to be x minus 2. And that's it, right? So there's a procedure that works. Well, there are many, many cases where you can't do it in your head. This one was easy. What if we have like several operations involved, divisions, multiplications, raising to power? That's not easy to do in your head. So we do it this way, and that's the inverse. All right, now let's talk about this number 8. So how do we find the inverse? Well, first we let y, f of x be y, right? And switch x and y. And then solve for y. So F inverse is x minus y. That's it. All right, let's do another one. Let's do number 12. This is a little more involved. So let's do number 12. So this is number 12. So the first thing I do, I write y equals to 2x plus 3 over 5x plus 4, right? And now I switch x and y. So x equals to, now we have x in two places, so we have to put y in both places, right? Now I have to multiply both sides by this denominator, right? So I get x times 5y plus 4 equals to, if I multiply this by this denominator, the denominator gets canceled, right? So I get what? I get 2y plus 3. Okay, so this was a step 1, this was a step 2. Now step 3 is to solve for what? For y. So basically we have to isolate y, but the y is in two different places. So what we have to do, we have to get all the y's to one side and then combine them. So let's see. X times 5y would be 5yx, right? Plus x times 4 is 4x. And then we have 2y plus 3. Okay, so I have a y here and I have a y here. I have to put them on the same side. I'm going to do 5yx minus 2y. I'm going to move this to this side and change its sign. Then I'm going to move this to the other side. So I have a 3 already on this side, and then minus 4x. So here, y is not by itself. Can we make it by itself? Yes. You have to factor it out. So if we factor the y out, we get 5x minus 2, right? If we take y out of here, get 5x. If we get y out of that, you get negative 2. And then 3 minus 4x. So y equals to 3 minus 4x over 5x minus 2, right? And that's it. So that is our inverse. 3 minus 4x over what? 5x minus 2, right? That's it. Now, if we graph this with a computer or calculator, let me graph these two. So I'm going to graph this one. Why do I have two of them? Let me graph this one. I'm going to do y equals to parentheses 2x plus 3 divided by parentheses 5x. See it down there, I'm writing, plus 4. See it over here. So that's one function. And then I'm going to do the inverse that we just found, which is that one. So let me graph y equals to 3 minus 4x divided by 5x minus 2 there. And also want to graph y equals to x, right? And now, so you see this is the red one, right? This is the red one, and this is the green one, right? Well, should be green. I don't know why it's not green. Let's make it green. And this one has to be red. All right, and I'm going to close this so we can get a bigger window. So you see the green one is one function, and the red one is its inverse. So as you see, they are symmetric with respect to y equals to x. You see, every point on the red one, let's say this point right here, if you connect it to, so let me use the pen. So this point right here, if you connect it to this line, go to the other side, you get a point, right? Every point on the green one has a friend on the red one here, right? Every point on the green one has a friend on the red one. See that? So they are actually symmetric with respect to y equals to x, and that is always the case. All right, so let's continue. That was number 12. So let's do one more. What is going on here? Let's do number 14. So in number 14 it says find the domain on which each function f is 1 to 1 and non-decreasing, and write the domain in interval notation, then find the inverse, okay, in the restricted domain. So we want to do number 14. So I'm going to do this one right here. So what aren't we doing? What don't we do? There we go. So now think about one-to-one function. We talked about functions that are one-to-one, or functions that pass the horizontal line test. For example, this one is not one-to-one because it doesn't pass the horizontal line test. This one is one-to-one because it passes the horizontal line test, right? So now, for example, this function right here, is it one-to-one? Well, let's graph it. We know how to graph that. That's just what? X squared moved to the right 6 units. So 1, 2, 3, 4, 5, 6. So it's kind of like that, right? Now, is it one-to-one? Well, obviously not, right? But can we make it one-to-one? Well, if you think about it, turns out that any function that is always increasing is one-to-one. And any function that is always decreasing also is one-to-one. So if we can, obviously this function is not one-to-one because it's decreasing and then increasing. So we can make it one-to-one. How can we make it one-to-one? We can just erase this part, right? Can we erase this part? and make it 1 to 1? Yes. What about this part? Can we erase this one and make it 1 to 1? Yes. But let's erase that part, right? So what do I mean by erasing? Can I just erase it? No, you have to do it algebraically. So here is what we do. We write f of x equals to x minus 6 squared, but we said the domain is from 6 to infinity. This way we don't have the other part. And the range of this is what? Is from 0 to infinity. As you see here, the range is from 0 to infinity. Okay, now we can find the inverse. So the inverse is, first we write what? Y equals to that. We switch x and y, right? So step 1, step 2. Step 3 is to solve for y. How do we solve for y? We take the square root of both sides, so we get plus and minus the square root of x equals to y minus 6. So y equal, let me put the y on this side. I'm going to move the 6 to the other side, but I'm going to write it on this side. So it would be plus and minus square root of x minus 6. Now here's the problem. We cannot write y equals to plus and minus square root of x minus 6 the same as f inverse. We can't say f inverse equals to that. Why? Because f inverse is a function and this is not a function. What's the remedy? Well, the remedy is to go back and remember that property that we said the domain of the inverse is the range of the function, and the range of the inverse is the domain of the function. So remember, these numbers are actually y values, right? So that means we're looking for the range. We want the range to start from 6 and go to infinity. So if we pick negative square root of x, we know the domain of x inside this radical is just what? From 0 to infinity. So if you start from 0, then this would be 0. And if you go to 1, this would be 1. And if you keep the negative here, the answers would be negative, right? We don't want that. We want the answers to be positive. So we need to get rid of that negative here and use the positive one. And if you graph the square root of x minus 6, right? That's, where do I put minus? Minus 6 should be plus, sorry. Because you move the 6 to the other side, it becomes plus. All right, plus 6. So if you graph this square root of x plus 6, you're going to get this right here. So you're going to get kind of like that. Now, this is the way I graphed it is not really to scale. So let me graph it with GeoGebra so you see the graphs are actually symmetric with respect to y equals to x. So let me graph x minus 6. Now what I want to do, I want to do it this way. You see, I'm going to put f of x equals to, and move this so I can see what is x minus 6 squared. So x minus 6 squared, right? And then I want another graph to be the other one, so I'm just going to call it g of x, right? And that was the square root of x, which is x to the power of of 1/2 and then plus 6. Right? So I just realized instead of moving on the y-axis, I just moved on the x-axis. So let me fix that. So square root of x, when you move it up 6 units, will be over here, right? Should have known that, but that's what it is. So so that's, you know what I mean, you see, that's it. So if you graph no wonder it didn't work. So see, square root of is not the square root of 6, you know, is not the square root of x minus 6, okay? I mean x plus 6 or x minus 6. So it's the square root of x plus 6. That's a what? That's a y transformation. So that's what it looks like. So look on the so on GeoGebra, it does a good job in terms of figuring out where the inverse is. But of course, this is not graph the way that we want it. So it's graphing what? It's graphing the green one over the whole domain. So there is a trick you can use. You can see, you can put if function. So if condition, and the condition we're going to put x greater than or equal to 6. Then what do? Then graph f, right? There. Now I'm going to turn off f, and you see, so that's part of f that we like, and this is its inverse. And now if you graph y equals to x, you see they're what? They're symmetric. Okay, let me close that so it doesn't use memory. All right, so where are we now? It was number 14. So let's do so in number 18 it says, what are we supposed to do? We're supposed to use function composition to verify that f of x and g of x are inverses. So what we have to do is use the property of inverses that we talked about. And the property of inverses that we talked about is what? Is the fact that f of f inverse is x, and also f inverse of f of x is x. Now we have to do both of these and make sure both of these are true, right? So these are the two inverses on number 18. So if these are inverses, then if I take f of g of x, I should get x. Now f of g of x means I take the input for f, and instead of x, I put this, x minus 5 over negative 3. Now obviously this is what? The negative 3 cancels negative 3, so we get what? We get x minus 5 plus 5, which is x. Check. Now, what about g of f of x? Now, g of f of x means you take the input for g, and instead of x here, we're going to put what? Negative 3x plus 1, plus 5. Negative 3x plus 5. So that is negative 3x plus 5 minus 5 over negative 3 over this is x. So check. Right? So this proves that these two are actually inverses. right? And now we can do number 20. It says, use a graphing utility to determine whether each function is one-to-one. So you just have to graph these. We can graph it using a calculator. Let's see. So we can graph it using, so let's do number 20. So cube root of 3x plus 1. That means we have to go to y equals 2 and go to 3x plus 1 and raise it to power of 1 over 3. That's cube root. And then go to zoom 6 or zoom 4. Oops, I did something wrong here. I'll put too many parentheses. There you go. So zoom 6. And it looks like it passes the horizontal line test. You see that? It doesn't cross the graph more than once. So we say yes. Based on what? Based on graph. All right, let's do another one. For the following, determine whether the graph represents a one-to-one function. 23 one-to-one? No, obviously, right? It doesn't pass the horizontal line test. What about 24? No, because if you draw a horizontal line here, for example, you have so many intersections, you see, here too. So no, it's not a one-to-one function. All right. So we want to do number 29. For the following, use the graph of the one-to-one function shown. Okay, so here's the graph, and what we want is sketch the graph of f inverse, right? So if you're given the graph of f, we can graph the f inverse, right? So this point right here is 2, 0. So we go to 0, 2. Let's say this point right here is 6, 2. So we go to 2, 6. And let's get another point right here. Let's say this point right here is 10 and what? And look, 2 point something. Let's say 2.5. So at 2.5, I go to 10. There. And then you kind of connect them like a curve, like that. Right? So that's the inverse, and as you see, it's symmetric with respect to what? Y equals to x, right? So all you have to do is switch x and y to graph the inverse. Okay? All right, and let's do number 30. Now number 30, we have the inverse. It says find what? Find f of find f of 6 and find f inverse of 2. Now, f of 6 means what? Means we need the output for the input 6. That means if the input is 6, what is the output, right? And we have to go to the function f. This is f. So we go to input 6. We find what? The output is 2. So this is 2, right? Now, what does this mean? F inverse of 2, it means that on the graph of f inverse, when the input is 2, what's the output? On the graph of inverse. So we go to this inverse one, and when the input is 2, what's the output? 6, right? So the answer to that is 6. We could also get it from here. We don't really need that if we have this. If we know that 6 goes to 2, then we know 2 goes to 6, right? Because what is that? You just switch these two. So this has to be 6. All right, and and number, let's say, number 34. So here it says, for the following exercise, evaluate. Number 34, what do we say? So in number 34, what we are told here is that f of 3 is 2. That means 3 goes to 2, right, under f. Now, what's f inverse of 2? Well, 2 goes to 3, obviously, right, if you switch them. And let's do a few more. Let's do 37, 8, and 9. These are numerical, right? So it says use the values listed in the table to evaluate or solve. So what is f of, I'm going to be able to write on this. So what's f of 1? So this is f of x, so these are the inputs, these are the outputs. So f of 1 is 0, right here. Now solve f of x equals to 3. What does that mean? Well, it means that if the output is 3, what's the input? That's what this is. F of x is the output of x. So we have x and 3. What is x? That's what it is. So we go to 3 in the output right here, and you see the input is what? 7, right? So solving for this, we get x equals to what? 7. And the last two I'm going to do are number 39 and 40. Find, with the same table, we want to find, well, let me get the table here, and then we go down and use that. So let's get the table. Okay. Now let's go over here and go to 39 and so 39 and 40 and 40. Well, let's go 39 first. So 39, it says what's f inverse of 0? Now, what do we mean by f inverse of 0? That means if the output under f, right, if the output is 0, right, what's the input? So what is that number? So x goes to 0, so where does 0 go? So we have to go to f and see where the output is 0. See that? So we know that 1 goes to 0 under f, right? So what's f inverse of 0? Well, it would be what? F inverse of 0 would be 1, right? So that's the f inverse of 0 would be 1. That's number 39. Okay, so let's do one more of these tables. Let's do number 42. It says for the following exercise, find the inverse function, graph the function and its inverse. Okay. Well, it's easy. I did a harder problem than this one, right? So I'm gonna maybe let you do this. So you set it up, y equals to 3 over x minus 2. Then you switch x and y. You get 3 over y minus 2. And then what? Solve for y. You just have to multiply by what? Multiply by y minus 2 on both sides, and then isolate y minus 2. So y equals to 3 over x plus 2, right? 3 over x plus 2. Now, if you combine these, you can combine them if you want to, or you can just write it like that, right? So that's what we're going to get. Well, I made another mistake here. I forgot to multiply by x. So this is, well, you don't have to actually know. That's good. Y minus 2, that's correct. You don't have to do this. Well, eventually you get the same thing. Okay, now if you combine these with the same denominator, let's say make it denominators the same. So this is like you're adding 3 over x plus, if you multiply by x and by x here, you get 2x over x. So if you make the denominator x, that's like 2x plus 3. And that's it, okay? So that's the inverse. And you can graph it again using the calculator, or you can graph it using GeoGebra, which is a free program you can download and work with. That's the inverse. Now, I could have edited the video so the little mistake that I made wouldn't show, but I don't want to do that because it's natural to make mistakes. So I'm not going to do that. So the little mistakes here and there happens, but if you know the concepts, you're not going to, completely flunk the test, whatever test it is, if you know the concepts. All right, so I think we are done with this chapter. That's the last thing I wanted to do. So I'm going to see you in the next video. Again, take care of yourself and others, and I'll see you in the next video.